Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem score after flipping matrix. Basically, we're given some rules of how we can flip portions of this matrix, and we want to maximize some score after doing that. So the idea is that we're given a binary matrix, looks like this, m by n. In this case, it's 3 by 4. Each row represents a number. It doesn't represent the number 0011, it represents the binary number, which we can get with 2 to the power of 0 and 2 to the power of 1, and these two are zeros, so we don't even count them. So our result is going to be 2 plus 1, which is 3. So this number actually represents 3. Now I'm going to continue with this just to give you a bit of intuition for this problem. If we were to do the rest of this number in binary, this would be 2 to the power of 2, and this one would be 2 to the power of 3. And that's assuming that these would be ones in that case. But basically what I'm saying is this is the 4's place. This is the 8's place. So think about this. Look at this. Isn't it true that the most significant digit is the most important, right? Like 2 is bigger than everything that comes before it, 4 is bigger than this, and 8 is bigger than this. And I know this intuitively very, very well because I know, like, if you have a binary tree, 1 node there, 2 nodes here, 4 nodes here, and if you just keep doing this, the bottom level is always going to have about half the size of the entire tree, and it's always going to be greater than the total number of nodes that came before it. So that's just how this works. So this is important to know because, again, we're trying to maximize the result. And for us to do that, first of all, to even calculate the score is to take every single number in here, convert it, let's say, to an integer. I think this is 3, this is, I think, 10, and I think this one is 12. We add all of them up, and we get, in our case, I think 25. That's not the result. We can actually improve it. We can make it 39. Let me show you how we can do that. First of all, we are allowed to look at any row and flip it. Flipping a row basically means changing every value. So from 0, we'd turn them into 1s. 1s can be turned into zeros. Now, you tell me, did that increase this or did it decrease the number? Well, we don't have to be super smart. We don't have to be super clever. We don't even have to convert this into the number just yet. We can literally just look at the most significant bit. Should we swap this or not? Well, if I swap this, I'm basically going to gain 8, so that's like plus 8, and worst case, I lose all of these 3. That's worst case minus 7, so I do come out ahead. So always flip if the first bit is 0. So row-wise, it's pretty simple. If that was the whole problem, this would obviously be a Leetcode easy. The problem is that we're not only allowed to flip rows, we're also allowed to flip columns. The idea is the same. Zeros will turn into ones, ones will turn into zeros, but this definitely makes things more complicated because we could have some rows and we might flip them, but then when it comes to flipping the column, how do we know that doesn't conflict with what we did earlier? First of all, how do we even decide how to flip a column? And then how do we know, like, which order to do this in? Well, let me kind of explain that part to you. So let's think about what we're doing when we are actually flipping a column. We did that with the rows. Like, we actually dissected that, and now we understand how to flip the rows. Let's try to see if we can notice anything similar about flipping a column. What are we doing when we're flipping any of these columns? When we flip this one, we're changing all of these to a 1. And so what we're doing is plus 1 every single row. How does that affect the result? Because that's all we care about. What's the final score gonna be? Well, the choice with this is actually simple. We only have 2 choices for every column. Either flip it or don't flip it. If we flip it, we increase the result by 3. If we don't flip it, well, it stays the same, right? So decision trees are pretty damn useful, I would say. And in the context of this problem, it makes it trivial because, well, it's going to get more complicated. Like in the second case, we have a choice. We flip it, we'd get a plus 1 here and a plus 1 here, but that's not really a plus 1. It's more of a plus 2 because this is the 2's place and this was the 1's place. This is the 4's place. So we do have to remember we're dealing with binary here, but this side will give us a plus 4, plus 2 here and a plus 2 here. And actually we'd minus 2 here. So this side would actually give us a plus 2, adding here, but removing this one. So basically 2 plus 2 minus 2. That's how I'm getting this. The other case is just leave it the same. So that's always 0. So as you can see, like if a column has more zeros than it does have ones, then we probably want to flip it because we're going to gain more than we're going to lose. Now, what happens if they're equal? Like if we had an equal number of zeros and ones, it doesn't really matter because these columns are obviously independent. I mean, this column, if it stays the same, it's not going to affect anything else. Whether we flip it or not, the only thing that we care about is how is it going to affect the final result. Okay, so if you agree with me that this is how we should flip columns, just looking at if they have more zeros than ones, this one has a single 0, so don't flip that. Don't flip this one either, obviously. Following these arrows, we will arrive at this matrix. Then we can take this and convert it into a number, which I will do like this. So like we're going to go through every position in this matrix, and for any given position, the row doesn't matter at all. We don't really care whether we're in this row or this row. The column does matter, and the column will basically tell us if this is a 1, then we want this to basically be 2 to the power of like the column. So in this case, it'd be 1. If this was a 0, we would just kind of skip it. We could say 0 to the power of that, but we'd probably just skip it. We'd just assume it's a 0. Don't do anything with it. The only thing is, how's this math going to work out? Because if we actually look at this matrix, this is column 0, this is column 1, this is column 2, and this is column 3. So raising 2 to the power of 2 is kind of weird. It doesn't really work how we want it to. What we really want is this to be 2 to the power of 0, this to be 2 to the power of 1, this to be 2 to the power of 2, and this to be 2 to the power of 3. So we kind of just want to invert the indexes, and we can actually do that. It's not too bad. We can just say 2 to the power of the number of columns. Let's just say that's this, and the number of columns is 4, minus 1, because we're starting at 0, and minus whatever the actual column that we're in right now is. So if you just want to test this out really quick, you can see here, this would be 2 to the power of 4 minus 1 minus 0, which makes sense because this is then 2 to the power of 3, which is the 8th place. If you want to try it on this one, you'll find it's 2 to the number of columns minus 1 minus c, which is going to end up being 0. So that's going to evaluate to 1. So the math does work out. You can check it if you want. Last thing, time complexity of this approach. We are going to modify this matrix in place. You can consider that constant extra space or n times m, where this is obviously dimensions of the grid. If you want to consider that as extra space, there is a more optimal solution that I will show you in just a second. But very, very quickly, I want to tell you how I know intuitively that this is going to work, that I know that the changing the columns is not going to conflict with how we change the rows first, because I want to emphasize we are going to change the rows first, and then we're going to update the columns. And very quickly, I'll explain why. We are being greedy. We are saying the result is going to be the sum of all of these numbers. Let's make them as big as possible. Each of them, let's make it as big as possible. We do that very easily when we update the rows because each number is only going to get bigger. It's never going to get smaller. We do the exact same thing when you think about it with the columns. We never will lower the result. We might lower some values, like look, we have a value here, here, and here. We might change this to a 0. So too bad. This number actually gets smaller, but we know for sure that this number and this number are going to get bigger. So the net change to the result doesn't get lower. It increases only. And that's how I know that this approach is going to lead us to the right answer. So I just got the dimensions of the grid. I like to put them in pretty descriptive variables. It helps me out. But now we're just going to have a bunch of loops. Think about what we said earlier. The first thing we want to do is swap every row if it starts with a 0. So we can say for r in range, for the rows, if the grid starts with a 0 at this row, then let's swap it. So we can do that with a loop. So we're going to go through every column in this particular row and basically just going to swap every bit. So I'm going to do that like this in Python. This is going to be a 0 if it's currently a 1, Otherwise, let's set it to a 1 if it's currently 0. So this is just the first portion. Flip the rows. Next, we are going to flip the columns. It's a little bit more involved. We are going to go column by column. So for C in range the columns, and we're going to count the number of ones, but I guess you could count the number of zeros. It doesn't really matter that much. Going through every row in this particular column, we are going to just total up the number of ones, as you can expect. Here, I'm just going to get the value at this grid row column position. If it's a 1, we increase this. If it's a 0, then it doesn't change, obviously. So that's what we want. We could have an if statement here instead of this, but I like to have it concise like this. We want to know, is there more ones than there are zeros? So I'm going to do it like this. The number of ones is obviously this. And is that less than the number of rows, which tells us how many values that we just looked at right now, which kind of reminds me, I don't know why I put columns over here. I'm sorry about that. This should be rows. Tells us how many rows we just looked at. This is how many of them were 1. How many of them are 0? Well, we can just take rows minus 1 count. That should tell us the remainder. And only if we have less ones than zeros, only in that case do we want to flip this column. So for this, it's not too bad. So for R in range rows, so every single value in the current column, grid row column, is going to be flipped the same way as up above. So it's going to be 0 if it's currently a 1, and it's going to be a 1 if it's currently a 0. Okay, so almost done. The only thing now is to actually convert this into the result that we're looking for, and I'll do that out here. Just going to basically iterate over the entire grid, and then the math is going to be the same as I kind of showed earlier. So we'll do this, add to the result this value, but one way I guess I could do this, and maybe this is the way you are thinking of, is if this value is a 1, then we could do something like this, add to the result 2 to the power of, I think, columns minus C minus 1, like I showed earlier. We could do this, or instead of having this if statement, we could actually just use the value itself, which is either going to be a 1 or a 0. And then we can shift it to the left by the above amount. So this is, if you're familiar with binary, basically the same as raising a number to the power of 2. And the good thing about this is we don't even need an if statement, because if this is 0, well, then this is going to evaluate to 0 anyway, so it doesn't matter. So that's why I kind of prefer the bottom one, but it doesn't matter that much. It just saves you one line of code. And down here, I'm just going to return the result. So this is the entire code. It's big O of n, m, time, and space. And on the left, you can see that it does work. It's relatively efficient. It's about as efficient as we can get this. So I wouldn't pay too much attention to the runtime, but we can actually improve the solution such that we don't use the input grid as extra space. And I'll kind of show you how we can do that. The idea is all about the score, right? All we want to do is update the score. Can we do that without modifying the input? Well, let's just give it a try. Let's just retrace what we did earlier and see what we can do to not update the input. When we started with rows, updating the rows, well, we can still do that partially in the sense that we can look at every value in the first column, and if it's a 0, we can swap that entire row. The problem is we don't want to actually store that data in memory. So we swap it. We don't necessarily have a way that we know of right now to remember that we swapped it or not, but at the very least, we know we changed the first bit from a 0 to a 1. And that's going to be true for the entire first column. It's always going to be all ones, right? We don't necessarily know about the rest of the grid, but this is definitely going to be all ones. How much is that going to contribute to the score? Well, it's just going to be each of these numbers, which is just 8 times however many there are. So mathematically, from just this part of the grid, we know for sure it's going to be the number of rows that we have multiplied by 2 to the power of the number of columns minus 1, because this is how we get like the number that goes here. 2 to the power of 3 is 8, and we have it this many times. Okay, so that much we know. It's not too bad. What about the columns? This is obviously where it gets more difficult. And this is why I think it's really hard to solve this problem like the way I'm about to show you without already knowing like what the solution is. Like I would not expect you to figure this out in a real interview. I think most interviewers definitely will not. If they do, they'll probably give you the hint that I'm about to give you right now, which is for every column column. Now we want to do the same thing that we were doing earlier. We want to flip if it has more zeros than it has ones. First of all, we might have like flipped some of these numbers. Like we flipped this number here. So these are not actually ones anymore. These are going to be zeros, and we're not storing that information inside of the grid. So how are we going to get around that fact? Like we don't actually know what is what. Well, ignoring this part for a second, I want to remind you that when we flip a column, all we care about is that there's more zeros than one. In other words, we only care about what the majority is. Like how many are ones and how many are zeros. Because let's say we have 3 ones and 4 zeros. Well, in that case, we swap these two, right? We always want the majority number to belong to the ones. So in other words, when we look at every column, all we care about is what is the majority count. It's 4. In this first one, it was 3. In this one, it's 2. In this one, it's 1. Actually, it's not 1. It is 2. The majority, there's 2 ones here. So that's all we care about. We care about that majority number because whatever it is, that's what we're going to swap into ones. So the majority tells us how many ones are going to be in this column and how many are going to be in this column and how many are going to be in this column. So this is part of the hint that I'm talking about. It's still not obviously easy to go from here to the solution I'm going to show you, but this is the big idea. The other problem though is that, again, we swapped this row, but we didn't swap the other two. So the majority is kind of messed up now, right? Like this is going to show as a 0, 1, 1, but that's not real. Like that's not true. Especially in this column, it's going to mess us up. It's going to tell us that there's more ones than there are zeros. So we do need a way to make this consistent. We don't need to necessarily be able to identify, is this a 0 or a 1, or is this a 0 or a 1? We just need to be able to differentiate them some consistent way. Well, this is the clever part. We can use the first row. Remember, these matrices that are here, we're not actually modifying the matrix right now. We only have this first original matrix. So keep that in mind. What we can say when we look at a particular position, for example, this is a 1. The reason we will know this is actually not a 1, this is actually a 0. You tell me, how do we know that? Basically, because the first bit is 0. Whenever the first bit is 0, we swap the entire row. So it's literally that simple. So now that's one case, obviously. The other case would look like this, where it's already a 1 and we have a 1 here. So in that case, this is a true 1 value, whereas this was a true 0. In this other case, we have a 1 here, but this is a 0. So this is also a true 0. Basically, since the first bit was already a 1, we didn't have to swap this row. So this is true. This is true. When we have a 0 though, and if this was a 0 instead of a 1, then that would mean it's really a 1. So if you want, you could probably draw like a table telling you all of those different cases. I think I'll do that. This represents what the first column is. For this input grid that we're given, this first column is pretty much the same. Current represents where we're currently at. Like for example, we're looking at this value. We want to know, what is the true value that goes here? Is it really a 0 or is it really a 1? This is enough information for us to know that. Right now, it is a 0. Is that the true value? Because we know that when we're calculating our score, our result, we've already made sure everything in this first column is a 1. So the true value that's here after this row has been flipped, and it's been flipped because it starts with a 0, the true value is a 1. True value over here is going to basically be, since this is a 0, again, we're going to flip this row. Therefore, this value is not going to be a 1. The true value is a 0. And you could do that for the rest of these. Like if it's 1, the true value is going to stay the same. Here again, the true value will stay the same. So we'll get 1, 0, 0, 1. Basically, the whole part about this is the pattern to notice is that when a particular value, whether it's this one here, or this one here, anywhere, if this one is the same as the first value in the same row, then we're going to consider it to be a 1. If it's not the same, we're going to consider it to be a 0. And we're going to count this just like I've kind of shown down here. We're going to have a count at the end. We're not going going to label it as ones and zeros because, as I've shown, it doesn't matter. The majority is what matters. So we're going to store whatever the majority is, and then we will be able to update our result like that. So we're going to go through this. Let me just kind of show you. We're going to go column by column. So I'm going to look at this column. This is different. So we're going to put a 0. We're going to keep this as 0, I guess. And then here it's different again. We're going to leave this as 0. Here, once again, it is different. So now if you were to think of it as two groups, we have one group with 0, one group with 3. Which one is the majority? Obviously 3. So then we'd update our result by taking 3 multiplied by this, which is 2 to the power of 0, which is 1. So it's just going to be 1 times 3. We're going to do the same thing with every column, just like this. Once you kind of know this, especially like this truth table part, I think that's definitely the most complicated, to just notice like this pattern here. And also just kind of knowing that the majority matters, the real values don't matter much. And this will save us space, so we won't have to update the input. Let's code this up. So the code for this solution is actually going to be a bit shorter. So we have our dimensions up above. I'm going to initialize the result not as 0, but I'm actually going to do what I showed earlier, which is basically rows. Like every first digit is going to be a 1. So we're going to say for every single row, we'll have 2 to the power of the number of columns minus 1. This is like 2 to the power of 3. Let's say that's 8, and we multiply that by every row. Now I'm going to go and return the result. Before we do that though, let's actually compute the result, and we'll do that column by column. So I'm going to say for C in range column. So now for this column, we want that count I was talking about earlier, because at the end, we're going to maximize it like this. We're going to say, okay, set this to the max of itself or the number of rows minus the count, right? We just care about what's the majority. And then that will go ahead and be added to the result. We'll take the count and let's say multiply it by the power. So let's just do 2 power. And this is kind of the math I showed earlier if you forgot, but it's basically like inverting the index. So we're going to take the number of columns minus C minus 1. So this is what we're trying to do. Now, of course, we do need to actually get the count. So this part is probably the most difficult to like come up with, but it's actually really easy to code up. So we're going to go through everything in this current column, and we're going to say if the grid here is equal to this. This is one valid way to do it. Alternatively, you could also have not equals, which I guess is kind of what I showed in the drawing explanation. But this just goes to show that it doesn't matter if it's equal or not equal. All we're trying to do is get a count, whether it's the count of zeros or the count of ones, and then just find the maximum of either of those groups. So basically here, this is the condition we're going to use to increment our count by 1. And I think last thing I'm missing is that since we already had this here, we can probably skip the first column. So this is the entire code. Let me just run it to show you that it works. It's not a lot of code, but it's definitely difficult to come up with. As you can see, it works. It's more efficient this time, but these are pretty random. Don't pay too much attention to this stuff. But again, don't let the code fool you. This was very difficult to implement like this. If you're preparing for coding interviews, check out Leetcode.io. Thanks for watching, and I'll see you soon.